So I should go ahead and get started. Assuming some people are not going to show up, I guess, but we only have like five people in here or four people in here. Oh, good, good. We got another one at least. So we're going to go ahead and get started. I need to finish up chapter 19, and there's quite a bit of stuff left in there. So I'm just going to jump right in. Uh, as I told everyone, I'll try to mention this again. Go ahead and chat me your first and last name if you haven't done so already. And I'm going to go ahead and share my computer screen with you for a second so we can get started talking about what we're talking about today. And that brings us to something called molar specific heats for gases and the equipartition of energy. So this is a table, and this is the whole reason I'm showing you this part of my book, part of the book, is because if you look at specific heats, they seem to have no rhyme or reason. Here's a monatomic gas, helium and neon. There's two of them, obviously. And there's something called specific heat at constant volume. That's why we subscript it V there. And there's specific heat at constant pressure, and that's sub P there. Uh, but you see that they seem to have no rhyme or reason. Like the 70.75 and the 0.148. Well, that's about twice as big, but 1.15, that's not half as big as this at all. Not only that, if you look at the other things, the diatomic molecules, you see no real pattern emerging. The triatomic or just polyatomic in general, there's no rhyme or reason. But if you decide to, instead of use specific heat per kilogram, because remember the specific heat is like calories or joules per gram or kilogram per Celsius degree. If we instead used uh, per mole rather than per kilogram or gram, then we get what's called the molar specific heat. And you can see that basically the molar specific heat, when we do that, we get basically a 2.98 for helium and neon, both with constant volume. And in fact, at constant pressure, we get helium and neon both having a specific heat of about 4.97. If we go to diatomic, we see 4.96 and 5.03. So those two are very similar. And 6.95 and 7.03, those two are very similar. So they look very similar within a certain atom type or a certain molecule type. And then if we look at triatomic, 6.80, 6.20, pretty close, not quite as close as the other two. 8.83 and 8.20, still pretty close, but not as close as the other three. And then you'd have to look at a bunch more to figure out if that's the case for polyatomic. But the main thing is there seems to be some kind of pattern associated with these specific heats when we deal with them in terms of molar specific heats. There's going to be a quantity gamma that I've already mentioned last time at CP over CV. And we're also going to introduce another quantity, CP minus CV, and you'll notice that this is about 1.99, 2.0, 2.00, 2.03, 2.0. All of those are about the same. So that gives us some indicator that these numbers are probably more important than these individual numbers. So in terms of that, let's go ahead and get started. I'm going to stop sharing this and start sharing my iPad. Uh, those of you, a couple of you came in, please chat me your first and last name so I know you're here. I'm going to go ahead and share my iPad screen with you guys now. If I can stop yawning, I apologize for that. Okay, so you should be seeing my iPad screen very soon. There you go. So, first thing I want to tell you is that the formula that we have instead of the formula that we've been using for heat to change the temperature is a little different, and I want to discuss that. So, this is molar specific heat. So, molar specific heat, it's indicated by being a capital letter. But one thing we have is the heat added to change a substance, specifically in moles of substance, with a specific heat at constant volume of CV, changing the temperature by amount delta T is given by Q equals N CV delta T at V equals a constant. Okay. Now, you might not even have any idea why this is so. I'm going to tell you in a second. But there's also another formula for Q, and that one's at constant pressure. So that's N times CP times delta T, and this is at P equals a constant. So when you have a constant, you might not think, or you might think, why would specific heat change? Well, remember that when you actually add heat to a system, a couple of things can happen. For instance, delta E internal is equal to Q minus W. So when you add heat, that heat can partly go into internal energy, which would indicate a partly an increase in temperature, but other things as well. But from looking at the first law, you can see that that heat could, in principle, be transferred to some kind of work, could be made to do work. But if you have work or specific heat at constant volume, then remember work has to be equal to zero. So when you use specific heat at constant volume, you're preventing the ability of the gas to do any work. So all the temperature, all the heat goes into increasing the kinetic energies that the molecules or atoms have, and not just the translational kinetic energy, but according to the equipartition theorem, every type of energy gets exactly the same amount. So, for instance, you might think of a diatomic molecule like we did before, where you have two atoms bonded together, and this is sort of acting like a spring. Now, you have translational motion in the x direction, that's v sub x. You have translational motion in the y direction, that's v sub y. And then you have translational motion in the z direction, that's v sub z. So that's three different energy categories. But with diatomic, you also have the ability of the molecule to rotate about this axis, so that's a fourth, to rotate about this axis, so that's a fifth. And then you have an energy associated with potential and kinetic energy due to the vibration. So we're now looking at six numbers or six different ways the energy can be distributed. The equipartition theorem is basically says that, hey, when you have a statistically random set of variables, for instance, like in this case, the average velocities and all those different coordinates, if you have six ways for energy to be distributed randomly under, n being on the order of 10 to the 23rd particles, then it's impossible for an appreciable fraction of that energy to be larger in one of those venues than the other. So V sub x will have a certain amount of energy. V sub y will have the exact same amount. V sub z will have the exact same amount. I omega squared about the vertical axis would be an equal amount. I omega squared about the horizontal axis would be exactly equal to the amount of energy that V sub x had. And then the kinetic energy that the vibration had would be equal as well. So all of those have an equal amount of energy, and that's what the equipartition theorem says. And that, for instance, was what allowed us to assume that v squared was the same thing as 3vx squared, because there's no reason to think Vy has a larger velocity than Vz. So Vx, Vy, and Vz should be equal in magnitude. Therefore, when you have V squared is equal to Vx squared plus Vy squared plus Vz squared, that's the same thing as 3Vx squared or 3Vy squared or 3Vz squared. So that's the continuance of that. Hopefully that makes some sense. Now, you might want to figure out, how do I actually get these specific heats? So the specific heat at constant volume is really the same thing as the specific heat that you had before, but now you're going to multiply it by the molecular weight of the substance times the specific heat at constant volume. And similarly, C sub P is going to be the molecular weight times lowercase c sub p, where the lowercase ones are the ones that are measured in joules or kilocalories or calories per kilogram or per gram. So that's how you get that. Remember, the molecular weight in this case is being thought of as having units of grams per mole. So you probably need to take it into grams first off. So you're using C sub P and C sub V lowercase in grams for best results, or you have to convert it to kilograms, one of the two. Okay. Now, if we have constant volume, oops, delta V equals zero, which implies work is equal to zero, which implies all heat added increases. I don't know, I just can't write that. Increases T and delta E internal. Okay. And really, all that matters with regards to specific heat is the change in temperature as a function of mass or whatever. So really, the change in temperature is all that matters when you're calculating specific heat. You don't care how much the kinetic or how much the internal energy is going up. You care how much the temperature is going up. So when you do specific heat at constant volume, all of the temperature goes to specific heat, or excuse me, goes to temperature and to increasing the internal energy. Whereas when you have it at constant pressure, then you can actually do work. So some of the heat can be lost to not affecting the internal energy and also the temperature, but rather the internal energy and the temperature and the work done. So that's why you'd expect in general CP is going to have to be larger than CV. We expect CP greater than CV because more of the Q goes to delta T than in the constant pressure. Again, that's because at constant pressure, some of the heat can go to doing work. So, with that in mind, we can start to think about at constant volume, Q at constant volume is just going to be the change in internal energy. That's from the first law of thermodynamics because W is equal to zero. Okay. Now, if you think about the constant pressure, oh, oh, then we have QP is equal to uh, delta E internal. Notice I am solving the first law of thermodynamics for Q. So when I solve that, that's going to be delta E plus W. So in place of W, I'm going to put P delta V because that happens to be the formula for work when the pressure is a constant. Work is equal to the integral of P dV, which equals just P delta V. Okay? So I have those two equations. And because of that, I can actually substitute what those values are from this equation right here and this equation right here. I can plug these in for QV and QP. So if I take that second version of, I'm going to do this in green. If I take that second version of the specific heat and the first version, or excuse me, the QV and the QP, if I want to talk about those, let's try doing this. Let's say QP minus QV. We expect that to be positive because the P generally takes more heat than the V does. But by saying this, we're going to say this is delta E internal plus P delta V, and then we're going to subtract from that delta E internal because that's what we got from plugging in the top two equations. So the purple equation for QV is plugged in here, and the blue equation for QP is plugged into here. But now I can use the first equations up at the top, and I will have, in fact, N CP delta T minus N CV delta T is equal to delta E internal. And the way you see that is because the delta E internal here cancels out with the delta E internal here. And the delta E internal, of course, we can say that is going to be just equal to, well, actually, no. I don't want to say we're using delta E internal. We're just using what was left after we subtracted those two, which is P delta V. So I'm going to write down P delta V like that, which can also be changed to NCP delta T minus NCV delta T is equal to P. And then the delta V, if we use the ideal gas law, we get solving for V, we get nRT over P. So I'd write this as nR delta T over P. And now you see that the ideal gas law has allowed us to eliminate P, and it's also allowed us to eliminate N, and it's also allowed us to eliminate delta T. And we come up with a really nice result that CP minus CV is actually just equal to R. And that was mainly what we're trying to shoot for because remember, one of the values of R was 1.99, which is exactly what we got on that table of CP minus CV. It was like 1.99, 1.99, 2.03, 1.99, 2.05, 1.98, that sort of thing. So what we've just found is a neat new expression that evidently CP and CV are related to R by CP minus CV equals R. And remember, R is equal to 8.314 joules per mole Kelvin, but that's also equal to 1.99 calories per mole Kelvin. So now we have that. Now let's look for what we can figure out about CP and CV themselves. So if I go ahead and start from delta E internal is equal to QV, then I can say, I'll start on the next page. So delta E internal is equal to QV. And if we talk about an ideal monatomic gas, then we know that this QV for an ideal monatomic gas, we end up getting delta E internal is just N times 1/2 mv squared bar, which is equal to just n 3 halves nRT, like that. Now, with that in mind, we can use that as well and compare that to QV. So now I can say N CV delta T, and technically this nRT shouldn't be nRT. Let me fix that real quick. The kinetic energy is 3 halves nRT, uh, but when you're talking about, yeah, I guess that's fine. Yeah, I just think we should probably write this as delta t. That would be better, just to accommodate for the fact that we're actually talking about the change in internal energy as opposed to the internal energy. The internal energy we knew was 3 halves nRT, but this is the change in internal energy, so we get 3 halves nR delta t. Now setting that QV on the left equal to E internal, I get NCV delta t is equal to, since that was QV, it's also equal to delta E internal, and therefore it's also equal to 3 halves N times R times delta T, which allows us to see that the delta T cancels out, that the N cancels out like that, and we've got yet another nice result, specifically CV is equal to 3 halves R. Now, we could do something similar with CV, with CP, and but we could also just use the fact that we found CP minus CV is equal to R implies, along with what we found out about CV, it implies that CP minus 3 halves R is equal to 3 halves, or excuse me, is equal to R, because that's what CP minus CV was. And of course, when I add 3 halves R to both sides, I get 2 halves plus 3 halves, so that's 5 halves. So I'm going to get CP is equal to 5 halves R. And of course, if you multiply 5 halves times R, which was essentially 2, then you're going to get basically 5 for the specific heat at constant pressure. And if you do that for CV, substituting 1.99, which is essentially 2, you're going to get 3. And that's exactly what we saw in that table of the specific heat, molar specific heats. So we now have some understanding why those values are that way, at least for the monatomic. We don't necessarily understand what it's going to be for the diatomic or the triatomic or the, the poly atomic. Sorry about that. Now, what we also need to understand is a graph that you'll see on page, let me see what page this is. I think it's 588. So let me stop sharing this screen for a second. We've got our major results, but now what I want to do is show you on that screen on in your book what we're looking at now. Come on. Okay. So this is a graph of the specific molar specific heat at constant volume. And specifically, this is the molar specific heat at constant volume as a function of temperature for a hydrogen molecule. So this is diatomic stuff, specifically H2. As the temperature is increased, some of the translational kinetic energy can be transferred in collisions into rotational kinetic energy, and at still higher temperature into vibration energy. Note H2 dissociates into two atoms at about 3200 Kelvin, so the last part of the curve is shown dashed. Also note that the temperature axis is logarithmic. So yeah, that is a big thing. But notice here, you basically have a constant amount of energy required at constant volume as long as you don't go over, let's say, around 70 Kelvin. Once you get around 70 Kelvin, things start to get a little dicey, and it jumps up from 1.5 R, which is 3 halves R, to lo and behold, about 2.5, which is 5 halves are. At that point, what's happened is you've gotten above 75 Kelvin, and around 75 Kelvin, what happened was the kinetic energy of translation was so large that it compelled some of the molecules to rotate rather rapidly. That's why it jumped up to 5 halves are. And then if you continue on to 1,000 Kelvin or right around 900 Kelvin, then the vibrational mode will kick in. So you start getting the vibration this way. And notice they're jumping up. It jumped from 3 halves to 5 halves. So that's 2 halves R that it went. So it's twice of 1/2 of an R. And what we've sort of figured out is we had 3 halves R for the internal energy because there were three modes of kinetic energy. There was the kx squared, there was the ky squared, and the kz squared. In the case of a diatomic molecule, we have the molecule rotating around this way, and then we have the molecule rotating around this way. Each of those, according to equal potential theorem, is going to give us the same amount of energy for each of those. So now instead of having three things for the energy to go into, we've got five of them, and each of them are going to get half of an R. So we've got 1/2 R for V sub x, 1/2 R for V sub y, 1/2 R for V sub z. That's the 3 halves R that you see for 75 Kelvin and below. But then once we reach 75 Kelvin, then we got rotation about a horizontal axis, and that's 1/2 R, so that brings us up to 4 halves. And then we got rotation about a vertical axis, that brings us up to 5 halves, which is exactly what this graph shows. Then if you go up to 1,000, what happens is we actually start to make the atoms and molecules do more of this. And in fact, that gets you yet another freedom. You get a potential energy, 1/2 kx squared, and a kinetic energy, 1/2 I omega squared. Each of those get a half of an R. So that's why we jumped up to 7 halves R. But as you get much higher, hydrogen gas will break apart, like they said, about 3,600 Kelvin. So that's why they put or 3,200 Kelvin. So that's why they put the dash lines there. Does that make sense to everyone? That's them showing the axes. So you can see this is about a horizontal, this one's about a vertical axis, and this one right here is about a horizontal axis. So that's the two modes of rotation that we got energized in this little band right here. And then these are what we got in this band. So the diatomic molecule can vibrate as if two molecules were connected by a spring. Of course, they're not connected by a spring. Rather, they exert forces on each other that are identical in nature, but of a form that resembles a spring force. So one person told me that the number of quantities squared types of energies that you have is what goes in the numerator. So you're looking at, some numerator over 2 times R. So if you have Vx squared, Vy squared, and Vc squared, there's only three, so that's 3 halves. If you have Vx squared, Vy squared, Vz squared, but you also have I 1/2 I omega squared for horizontal, and then you have 1/2 I omega squared for vertical. That's another 1/2 plus 1/2, so that gives you 5 halves. And then you could have 1/2 kx squared for the vibrational potential energy, and then you have a 1/2 I mv squared for the vibrational velocity. So that brings it up to 7 halves. All right. They talk about solids here. That's good stuff for you to read for concepts and to better understand. I also wanted to point out that the table we looked at earlier, so we got CP minus CV was R, and you can see right on the money, 2.0, 2.0, 1.99, 1.99, 2.03, 2.05. So that's pretty good. We also got that CP was 5 halves and CV was 3 halves. And of course, 3 halves would mean essentially three, and 5 halves would be essentially five. And you can see, sure enough, it's five right here for CP, and it's three right here for CV. So all of this is at least consistent with the diatomic. All right. Any questions on that? All right. So now what we're going to do is derive some things that happen as a result of this, if I can find my Zoom window, come here, Zoom. I'll go ahead and stop share. Hopefully it'll pop up. There it is. I got so many windows on my desktop, it's hard to see. All right, so now I'm going to go ahead and share my iPad screen with you guys again. All right. So now what we want to do is we're going to derive that expression that I told you about adiabatic gases. Remember, P times V to the gamma power is equal to a constant. I think I wrote it like P1 V1 to the gamma power is equal to P2 V2 to the gamma power. That's what we're showing you here. So I'm going to start off with adiabatic expansion. And remember, adiabatic means Q equals 0. Okay, so there's no change in heat. And in fact, we can start off with the first law of thermodynamics. So if I start off with the first law, I get delta E internal is equal to Q minus W. But since it's an adiabatic expansion, Q is equal to 0. So instead of having Q minus W, I just have minus W, which we can write as well, you could, in principle, treat it as if it were a differential. That's one way of looking at it. So let's try that. We're going to go ahead and say dE internal, which remember that's an actual true differential because E is an equation of state and therefore it's a state variable and you can have an actual function that's represented as E, but you don't really technically have a function that's written as Q, so you can't write a dQ. You really have to write a dW, a d bar Q or a d bar W. So in this case, it's going to become d bar W. But in principle, we do know a formula that we found from work equals the integral of P dV. We could say that this is going to be equal to negative P times dV. So that's an expression we can use. We also know that when we deal with heating up a gas at constant pressure, or excuse me, at constant volume, then dE internal, since it's at constant volume, is ultimately just going to be Q. But if I use what we know, the dE internal is going to be a result of heating at constant pressure, or excuse me, at constant volume. So that's going to be N CV times delta T. Now I can plug that in for the dE internal that I have above, so I can use that and I can use this. And when I do that, I get N CV delta T is equal to negative P dV like that. That can also allow me to write this as, uh, let's say, N CV delta T plus P. And actually, let's do a dt because it's going to come in handy to write it as a differential anyways. So I'll do that. So CV delta T plus P delta V, that's all equal to 0. That's what we did with constant volume. We can do the same thing with constant pressure, and we can also treat the ideal gas law separately. So if we take P V equals N times R times T, if we consider taking a differential of that, the left-hand side is a product rule. So we'd have to say P times the derivative of the second plus the second V times the derivative of the first, which would be dP, and that's got to be equal to N times R. Both of those are constants as long as we're dealing with a sample of gas that none can escape, and then that would equal dT. So there's a differential version of the ideal gas law. And this is what I was warning you about in your steam table thermodynamics. When y'all take engineering thermo, it's going to be, well, it might be steam table, it might not be. But the main thing is you're going to do a lot of derivatives. So that's sort of what we're looking at right now. And we should be able to combine these equations. For instance, I can actually take the PDV and sign the or solve all this for NR dt, or specifically just for dt. So if I solve this for dt, I get P dV plus V dP, plus V dP over N times R. I could do that, and now I could plug that back into the equation we had above. And in other words, I'm going to take this and I'm going to plug it in here. So now I'm going to have N CV times P dV plus V, I don't know why I keep writing that, dP over N times R plus P dV is equal to 0. You can see immediately that the N down here is going to cancel out with the N down here, and we can get some more simplification by distributing. I'm going to, let's see. Yeah, I think I'll go ahead and multiply through by R on everything. Let's go with that. We're going to say, now I'm going to say CV times P dV plus CV times V dP plus, all this should be over NR, plus P dV is equal to 0. And we can, oh, the N was gone, so I should erase that. It's just the R down here. Okay. So I can simplify a little farther. When I do that, I'm going to get, uh, let's go ahead and copy this to the next page. Copy, paste. So now what I can do is multiply through by R. And when I do this, I'm going to change colors now. I'm going to have C sub V P dV plus C sub V. Whoa, that's some dyslexia there. CV, that's a weird kind of dyslexia, times dP plus R P dV is equal to 0. Now what you can see is we have a common PDV term. Specifically, we have this PDV and this PDV. So we can go ahead and write CV plus R times PDV. That takes care of that term and that term. And then we have plus CV times V dP is equal to 0. So that's an expression we're looking for. We can also use the fact that CV plus R from CP minus CV is equal to R. We can see that CV plus R is actually equal to CP. So now I can say CP times PdV plus CV times VdP is equal to 0. And that was almost what I'm going for. Now what I'm going to do is multiply both sides by 1 over CV. When I do that, I get CP over C. Ooh, my C looks really bad there. CP over CV times P dV plus V dP is equal to 0. Now we can go ahead and simplify this by defining that quantity Cp over Cv, and that, I don't know why I keep turning that C into a D. So that's going to be our definition of gamma. So now we're going to say gamma P dV plus V dP is equal to 0. And from that, we can divide both sides by P and V. In other words, we're going to multiply top and bottom by 1 over P V. And what you're going to see is that we get gamma times dV over V plus, in the case of the VDP, we're just going to get the V disappears and I'm going to get dP over P, and that's all equal to 0. Now, if I wish to integrate this, then I could do gamma, pulling that out in front, integral dV over V plus integral dP over P is equal to the integral of 0, whatever you wanted to do, basically. So in this case, we're going to get an integration constant that comes from each of these indefinite integrals, including the one on the third. But I'm going to put all the constants on the right-hand side, and what I have is gamma times the natural log of V plus the natural log of P is equal to some constant. And of course, we also know that when you have a number multiplied by a len, you can use that number to become the exponent of the argument of the len. So we're going to say the len of V to the gamma power plus the len plus the len of P is equal to a constant. And from that, we can realize that when you add two natural logs, that's the same thing as multiplying the two arguments. So what we've got is the natural log of P times V to the gamma power is in fact equal to a constant, like that. And that tells us that in fact P times V to the gamma is equal to a constant, which is what I advertised before. So that's how we go about getting that P times V to the gamma power is a constant. Now we're able to actually do an example. So let's look at example 1915. I'm going to read it to you, but it might come in handy if you're looking at it at your book as well, because there is a graph. I'm going to try to draw the graph as neatly as I can. This is going to be a P versus V diagram, and V is in cubic meters and P is in kilopascals. And what we have is 200 here, and then 100 here, and then we have 0.50 here. Actually, I should make that a little bigger. I'm going to change this, make the 0.5 be, let's see, right here. Oop. And that's 4 spaces over, so that means the 1.0 is going to be here as well. And what our graph is going to look like is we're going to have a graph that goes from this. I'm trying to show all these different lines to help us a little bit. I'm going to start off up here at C, and actually I'm ending there technically. Oh, the arrow goes that way, so I'm actually ending there. And then I'm actually starting here. Those are our points. And they're saying this line right here is an adiabat. That's what you call the line on a PV diagram that corresponds to a adiabatic process. You call it an adiabat, and you call this one an isotherm. So the question says an ideal monatomic gas is compressed starting at point A in the PV diagram below, where PA is equal to 100 kilopascals, VA is equal to 1.00 cubic meters, and TA is equal to 300 Kelvin. The gas is first compressed adiabatically to state B, which has a pressure sub B equal to 200 kilopascals. The gas is then further compressed from point B to point C, where VC is equal to 0.50 cubic meters in an isothermal process. Determine VB and calculate the work done on the gas for the whole process. So A, they want VB equals question mark, and B, they want to know the work done from A to B, or A to C. That's what we're looking for. What we have in terms of data is we've got PA is equal to 100 kilopascals. We also have VA, which you can get from the graph, of course, is 1.00 cubic meters. And we have TA is equal to 300 Kelvin. We have PB is equal to 200 kilopascals. And we have VC is equal to 0.50 cubic meters. So that's the data we have. What we'd like to do is figure out exactly what VB is. So if we want to start that, we can realize that since it's an adiabat from A to B, then we have for A to B, we know that P sub A times V sub A to the gamma power is equal to P sub B times V sub B to the gamma power. And what we're looking for is P sub B. So what we can do is divide both sides by PB, and I'll get PA over PB times VA to the gamma is equal to VB to the gamma. So then I want to raise both sides to the 1 over gamma power, like this, and that will give me VB is equal to PA to the 1 over gamma. Actually, I'll say it PA over PB to the 1 over gamma times just plain VA. So our gamma power, remember, our gamma is defined to be CP over CV, and CP was 5 halves R, and CV was 3 halves R. So the 2's are going to cancel out, and I end up getting 5/3 for gamma. So now I'm going to take the pressure at A, which is 100 kilopascals, divided by the pressure at B, which is 200 kilopascals, and I'm going to raise them not to the 5/3 power, but to the 3/5 power, because that's what 1 over gamma is. And then I'm going to multiply that by the volume at A, which is 1.00 cubic meters. So if I take 0.5, which is what 1 divided by 2 is, or 100 kilopascals divided by 200 kilopascals. If I take 0.5 and raise it to the 3/5 power, which is 0.666, then I get 0.6299 6. And then I'm going to multiply that by 1, which gives me, obviously, 0.62. I might as well call this 630. And that's 3 sig figs for everybody, so I'll do that, and that's in cubic meters. So that's what our volume at B is, which is the first thing we're supposed to ask. Now, the other thing we're supposed to ask is, or we're supposed to answer, is to figure out exactly what the work done is. The pressure P at any instant during an adiabatic process can be solved using this adiabatic thing formula. So we can do that, and we just have to do, well, we just have to do work equals the integral of P dV. So in this case, we need work from A to B, which equals, in this case, it's an adiabatic process. So we can represent the pressure as, I'll just take it over here and write it on the right. We have P V to the gamma is equal to PA VA to the gamma power. So the final pressure P should be PA times VA to the gamma power over the arbitrary V to the gamma power, like that. So now I can write PA times the integral VA. I could have written this out in front of the radical as well, or in front of the square root as well. And now I'm going to have dV over V to the gamma. So this part becomes PA VA to the gamma times the integral V to the negative gamma dV. And of course, what we do when we integrate a variable to an exponent power is we add 1 to the exponent and then divide by that. So that's going to give us PAVA to the gamma, and then we're going to get V to the negative gamma, but I have to add 1 to it, so it's going to be plus 1, and that's all going to be divided by negative gamma plus 1, like that. So we can now say the work for this part is PA, which is 100 kilopascals. So I'll say 100 times 10 to the third. Oops. 100 times 10 to the third pascals times VA, which was the 1.00 cubic meters. Now remember, a pascal is a Newton per square meter. So when you take a pascal and multiply it by a cubic meter, you end up getting a Newton meter, which is a joule. So that part's just a joule. And now I'm going to evaluate this V gamma minus 1, or excuse me, the V to the negative gamma plus 1. I would have to evaluate that at the two end positions, A and B, because that's where we're actually going. And this negative gamma over, plus 1 is going to be negative 5/3 plus 3/3, gives me negative 2/3. And then I'm going to take and say VB, because that's the final one, to the negative gamma plus 1 power minus VA to the negative gamma plus 1 power. So this is going to be negative 5/3 plus 3/3 is negative 2/3. So this is going to be a negative 1.5, because 3/2 is 1.5, times 100 times 10 to the third. This gives me negative 1.50 times 10 to the 1, 2, 3, 4, 5. Now, the VB to the negative gamma power, that's supposed to be the 0.630. Anybody confirm that answer, by the way? Your book said it was 0.66. I got 0.63, and it seemed okay. I didn't see any mistakes, but it might have been how I chose to do my 3/5. Oh, no wonder. I did 0.666 instead of point 0.6. So yeah, that should probably be the 0.63. Uh, I'll just write that. Okay. So I can fix that on the fly. Just call it 0.66 instead of. Let me do that again. I'll just do that calculation real quick. Zero point 0.5 raised to the zero point 0.6 power, and that gives me 0.6598. So that's what I should use here instead of 0.63. So that's the right answer. Sorry about that calculation error. I'm glad I figured that out in real time anyways. So now I'm going to take the 0.6598 and I'm going to raise that to the that should be to the negative two-thirds power. And then I'm going to take the VA, which of course was 1.00 cubic meters, and I'm going to multiply that or raise that to the negative two-thirds power as well. And I don't know why it's part purple and part blue, but we're going to go with it. Okay. So if I raise this 0.659 to the negative up 0.6598, and I'm going to raise that to the 0.66666. Oh, it's supposed to be to the negative 0.6666. Oops, I just erased it all. That was smart of me. 0.6598 raised to the 0.6666666 gives me 0.75789. And of course, 1 raised to any power is going to be 1.00. And of course, this part in the front came out to be joules, Newton meter squared, yeah, Newton meter. And then these units, technically, yeah, that should be fine. So when I do this, I get a work that's equal to 0.75789. And that gives me basically the work done here times 1.5 times 10 to the fifth gives me 3.632 times 10 to the fourth joules. That's the work from A to B. Now I got to figure out the work from B to C. The work from B to C is equal to the integral P dV, but this time it's at constant temperature because it's an isotherm. So I can substitute in N times R times T over V dV, integrate that, and I'm going to get N times R times T times the natural log of VB over VC because that's where I'm integrating from VB to VC. So with this in mind, I got N, which was, it was 1 mole of gas if I remember correctly. I think, or I might not have had to. Yeah, that's it. I don't know what the moles are, but I can get rid of that NRT a little bit later. So what I want to do now is since the NRT is a constant, I can use PB times VB because that's also true for ideal gases. PV equals N times R times T. When it's isothermal, that just means P1 V1 is equal to P2 V2. So I could use PAVA in place of NRT, or I could use PBVB in place of NRT. All of it doesn't matter at all. What I'm going to do in this case is I got work is equal to the integral of PdV, and I'm going to go from B to C. I'm trying to figure out why anybody did any kind of negative. For isothermal process B to C, the work done at constant pressure. So the pressure at any instant during the process is now that's all looking good to me. I don't know why they had a negative in there. Okay, so let's go ahead and compute this. And actually, I want to look at that. I want to look at the graph again real quick just to make sure. Okay, so I did get about 37 kilojoules for the last part, and that seems about right. In this case, we're actually using uh, negative nRT. So you're going to ultimately say this is P negative PB VB times the natural log of, in this case, it's going to be, oh, okay, I see. So they had a negative, but they just are doing it kind of weird in that, oh, I put my VB and VC upside down, so that might be the difference. So I'm going to say it's negative PB VB ln of VC over VB. So that ends up working out the same way. So this is going to be negative, and then our pressure at B, of course, was zero point 0.5, if I remember correctly. No, 0. Oh, that's the B. That's the one we did derive for. So that's 0.6598 times the volume at B, which was the volume at B was what we solved for. That was 0.65. It was the pressure that I stupid hid. So the pressure at B was 200 kilopascals. So 200 times 10 to the third Pascal, and then 0.6598 cubic meters for VB, and then the natural log of VC, and VC is 0.50 cubic meters divided by VB, which is 0.6598 cubic meters. So I can take the natural log of zero point 0.5 divided by 0.6598 in parentheses. That gives me a negative number, which is going to make this a positive. And then I'm going to multiply that by 0.6598 times 200 times 10 to the third. And that gives me 3.65, actually 3.660 times 10 to the fourth joules. I don't know where I wrote a W there. So now the total work is equal to the work done from A to B plus the work done from B to C. And that is going to give us 0. Let's check this number over here. How did I get that? Uh, I'm disagreeing on this number right here. The point 3.6. Did anybody double check my calculation on that? Point 6598. I'm going to raise that to the negative point 6666666. Ah, there's a problem. So there was a calculation error in here. This is 1.31. I think I left off the negative. That might have been the problem. And this one's just 1.00. And it is to the negative two-thirds, right? So negative five-thirds plus three-thirds is negative two-thirds. So that does seem right. But that would give me a negative amount of work too, wouldn't it? Oh, I forgot that negative sign to begin with. All right. So, with this in mind, this gives me an entirely different number. So 1.3194 minus 1 is 0.3194 times 1.5 times 10 to the fifth. There it is. So this gave me 4.791 times 10 to the fourth joules. So that's basically 47 kilojoules plus 37 kilojoules. And that gives us, of course, 47 plus 37 is 70. That'd be 84 kilojoules equals work total. All right. So that's the a problem that we've just solved with regards to the adiabatic process using the PV to the gamma power. Uh, One thing I did do is I got a little fast and loose. You're talking about pressure here, and it's a matter of the pressure of the gas versus the pressure that's being done on the object versus by the object. So I completely left off all the negatives. That's why both of these came out negative, but I ended up just changing the sign to the negative, all because again the work done here is the difference of the work that we use from Newton's first law or from the first law of thermodynamics. It's the work done by the system, not the work done on the system. So we're going to have to use the negative of that. That's where that negative sign came in. But that basically gives you the same result, roughly 84 kilojoules. Any questions on that? This is not my good work. I don't know. I did it last night. It must have been I must have waited too long between last night when I did it and reviewing it because if I would have reviewed it better, it would have come out a little smoother. But anyways, you can look at it. It's example 1915 on around page 560. So you should be able to figure out what that is. The last thing we want to do is I need to work on heat transfer, and there's three types of ways that heat can be transferred. Heat can be transferred by conduction, which notice the duck sounds a little bit like touch. So that's what I used to use to remind myself what conduction is versus convection. So conduction is when two things are touching. Convection is when you sort of think of a coffee maker. If you've ever seen how a coffee maker works, it has a little device at the very bottom that's a temperature uh, it's basically a chunk of metal that current runs through and it gets hot. Element is the word I was going for. So that actually would heat up the water. That makes the water around it get warmer. But when water gets warmer, other than that weird spot at 4 degrees Celsius, normally when water gets warmer, it expands. And when it expands, that means it becomes less dense, so it floats to the top. In expanding, it's also cooling off a little bit, but it's still warmer than it was. And when it gets to the top, it can deliver its heat to whatever it's the top of the water. Then that once it's delivered that heat, it's going to lose some heat and condense again and fall back down and get to go through another round of being heated by the element. So that's what convection is basically allowing currents to go up and down. And then there's radiation, which is basically just, we actually call, other types of radiation. There's particle radiation and stuff like that. That's totally unrelated to this. But radiation is electromagnetic radiation, specifically a electric field that oscillates in one plane, a magnetic field oscillating perpendicular to that, and then the actual wave that that is the electric field this way and the magnetic field this way, that velocity of that electric and magnetic field is perpendicular to both of those directions, and that's what radiation is. We don't really have much in terms of equations to help us with convection or radiation. Radiation will come more in the 242 class, but right now we have the ability to do conduction. So the equation that we use for conduction is this one, and it basically says the heat added per unit time is directly proportional to, let me draw a diagram real quick so you'll have some idea what kind of figure this applies to. So you can imagine, for instance, that this is a hot reservoir, what we call a heat reservoir, and that means basically it's so big that even when you lose heat, the temperature doesn't change. So that's the main thing. So I'm going to call this temperature T1. And as I said, it is a heat sink or something they might want to think of it as. And it has an area A at the end of this little tube. And this little tube is a solid tube, if you will. At the other end of that is also an area A. And this heat reservoir or heat sink is at temperature T2. So this is another heat reservoir. And this reservoir, of course, stays at a constant temperature T2. And what we see is the heat flowing through that object, since T1 is greater than T2, the heat should flow this way. And that heat flow should be directly proportional to A. Like if you want to take your significant other when you've been out playing in the snow and your hands are real cold and you want to make them feel the cold, you don't just touch them with a fingertip. I mean, that's cold. But if you lay your whole hand on it, then you feel a lot worse because it's directly proportional to the surface area of the thing that's actually propagating or pushing out the heat. Or another way of thinking of it is if you put a big pot of water to boil on a little burner that's that big, it's going to take a lot longer than when you put it on a burner that's as big as the bottom of the pot. So we do see that the temperature or the heat transferred from the hot reservoir to the cold reservoir per unit time is directly proportional to the area. I would say it's also directly proportional to the change in temperature from one side to the other, and it's also inversely proportional to the length of the rod that it's going through. So you might recognize this end part right here is really a temperature gradient. It's basically dt, where the numerator T is capital T for temperature, and the bottom T is lower. The bottom T is X or T for thickness, but you could use just plain X or something. So this would be dt over dx or something like that, and that's what we call a gradient. Now, you can also add a constant of proportionality that would actually make it into an equation, but when we do that, that would be the end of it. But guess what? It also matters what that little cylinder that that the heat's traveling through, it matters what that is made of. So what we're going to do is introduce a new constant that absorbs that as well. So now I'm going to say Q over T is equal to some constant times A times T1 minus T2 divided by L. So I will say that the quantity L over K is what we know of as the R value. So if you've ever been on a construction site and seen insulation hanging on the walls, still it'll have like R-19 or R-13 on it. R13 is sort of the bare minimum a wall can have by code. So you put in R13, but that R value means L over K. So if you wrote this as uh, 1 over L over K times A times T1 minus T2, then you could also write it as A T1 minus T2 over the R value. And that's the one we use in construction, but you're not going to mess with it too much. It tells you about the units and all that good stuff. But the main thing we care about is this equation right here. Okay. And you could make it a differential equation if you wanted by saying dq over dt is equal to, in this case, you're going to say a negative k times a times dt over dx. And they're saying negative here because it turns out that as the temperature uh, increases, the amount of the as the temperature gradient decreases, you actually get more heat going through it or something along those lines. The main thing is we're going to use the Q over T equals K A over T1 minus T2 over L. And as an example, your book gives you thermal conductivities. That's what the K is called. Thermal conductivity. And for instance, for silver, the thermal conductivity in joules per second per meter per Celsius degree is 420 joules per second per meter per Celsius degree. Water, for instance, would be 0.56, meaning it's not very conductive, and meaning silver is quite conductive. In fact, silver is the highest that they listed on here, and air is on the order of 0.023. Same units used in that. Okay. So they give you a really straightforward example, example 1916. And it says a major source of heat loss from a house in cold weather is through the windows. Calculate the rate of heat flow through a glass window 2.0 meters by 1.5 meters in area and 3.2 millimeters thick. If the temperature at the outer surface is 15 and surfaces are 15 degrees Celsius and 14 degrees Celsius. Okay, so we're going to say T1 is 15.0 degrees Celsius and T2 is 14.0 degrees Celsius. And what else can we say? Oh, the area is equal to 2.0 meters by 1.5 meters. And the thickness L is 3.2 millimeters. So we're able to calculate this. What we want to know is the heat flow. So that's a certain number of joules or calories per second. So Q over T is going to equal K, and K is for glass. And according to that table for glass, that's 0.84 with the units. So 0.84 joules per second per meter Celsius degree times the area, which would be 3.0 meters squared, times the change in temperature, which is 1.0 Celsius degrees, over 3.2 times 10 to the negative 3 meters. Now you can see that the 2 meters in the bottom cancels out with a meter squared in the area, and all we get is 0.84 times 3 times 1 divided by 3.2 times 10 to the negative 3, and that gives me 787.5, which is more sig figs than we have, obviously. And that comes out in joules per second or watts. Now, windows actually do take the majority of the heat loss in a house, and that's a big part of calculating uh, the tonnage of your AC and heating unit, for instance. But to be honest with you, it's a little misleading if you actually had, what the temperature is outside of a window versus the temperature inside a window. They said 14 and 15, which makes you think it's a really small quantity. But that's because we found experimentally that on low wind days, generally there's a little cushion of air just outside of the window that stays there, and it's usually some temperature between air temperature and the indoor temperature. And then there's another wafer of air on the inside of the window that's a little bit closer to the temperature of the window and what's outside the window than inside the house. So that little wafer of air on each side actually provides a modicum of insulation to make the windows a little less awful. So, anyways, that's it. We have now completed chapter 19. Next time we'll go into chapter 20. There is an equation. Actually, I should probably. It's there is an equation called the Stefan-Boltzmann law, and that last example, y'all can check that out yourself. But that is covered, even though I didn't necessarily cover it in this lecture. But we're done. You guys go have a good day, and call me if you need anything, or actually text me if you need anything. But have a good day. Thanks for coming. I'll wait for the last person to leave in case anybody has any questions. Those of you who came in late, don't forget to chat me your first and last name if you didn't already. Thank you, folks. Sorry about the mix-ups and all this. I did a bad job. It's horrible. All right, that's it.